In this podcast, we will be looking at writing net ionic equations for different types of reactions. So we'll take the samples first, examples given here, and then we'll do some sample problems. So if we go back to the first type of reaction, which is combination or synthesis reaction, the first problem here says sodium metal reacts with chlorine gas to form aqueous sodium chloride. So when you start writing it, when they say sodium reacting with chlorine to form aqueous sodium chloride. Now you know sodium being a metal will be Na, and you don't have to write the states. However, it helps clarify things in your head if you write the states. Chlorine, you know, is one of the half Brinkel gases. It exists as diatomic. When they say chlorine, they don't mean Cl, it's Cl2. And when sodium and chlorine combine together, they'll form an ionic compound, sodium chloride. And how do you figure out what subscript should go here? These are the charges. Chloride forms -1 and sodium forms +1, so it's NaCl. Now let's balance it. You put a 2 here and a 2 here. Now this is complete molecular equation, and you have to see, to make it net ionic, dissociate everything that can be dissociated. Sodium being element cannot be dissociated further, chlorine cannot be dissociated further, and sodium chloride, because it's in aqueous solution, will break into sodium ion and chloride ion. And now see if there's anything you can cancel. A common mistake, sometimes kids will tend to cancel out chlorine, Cl2, with chloride. No, you can't do that, because chlorine is a molecule and chloride is an ion. They are two different species. So the net ionic equation for this reaction will be this. Now let's take some sample problems so that they're new to you. Let's work on these together. Calcium is heated in nitrogen. How would you write calcium? Ca. Nitrogen, again being a half Brinkel gas, will be N2, and you know it'll form calcium nitride. Nitrogen tends to form 3- and calcium tends to form 2+. And when you crisscross charges, what do you get? Ca3N2, and that'll be solid, because ionic compounds are solid unless they say that it is aqueous solution. So your balanced reaction here will be 3Ca plus N2 gives you Ca3N2, and you will not be breaking calcium nitride because they don't say that it's an aqueous solution. So this is the net ionic for the first one. Now for the second one, sodium oxide is added to water. What is the formula for sodium oxide? Na2O. How do you get that? Because when you crisscross it, oxygen forms 2- and sodium forms 1+, and you add it to water. Now you got to remember, when a metal oxide is added to water, it forms metal hydroxide. Which metal hydroxide would it be? NaOH. Let's balance it. If we put a 2 here, we have 2 oxygens, 2 hydrogens. It's all balanced. Now let's start looking at net ionic equation. What can be broken? So sodium oxide is added to water. So sodium oxide here is solid. They should have specified, but default is solid. So you have solid sodium oxide and you're adding it to water. When you're adding solid sodium oxide, at that time sodium oxide is not present in dissolved form. It's solid. So you keep it together. Water is always left together, and NaOH being a strong base will be dissociated. So let's write the net ionic equation. It'll be Na2O plus H2O gives you 2Na plus 2OH minus, and that is the net ionic equation. Let's look at the third sample here. Phosphorus 5 oxide, P2O5, is added to water. Again, this is a molecular compound, won't break, molecular compound, won't break. Now you have to think reaction prediction. When a non-metal oxide combines with water, it forms an acid. In this case, it will form phosphoric acid. Oftentimes, kids ask me, couldn't it be H3PO3? And my answer is, yes, it could be if you could balance it. You wouldn't be able to. So the way you balance it is with H3PO4 and 5 6, 7, 8 of oxygens, and then you have 2 phosphorus and 6 hydrogens. Now when you write net ionic, it will be this. You will not be dissociating phosphoric acid because it's a weak acid. So that was some samples of combination or synthesis reactions. Now let's go to decomposition reactions and write the net ionic equations for some of them. Ammonium carbonate is strongly heated. Remember, before you can predict what will be formed, you must memorize these bullet points here. When an ammonium carbonate dissociates, it forms ammonia, water, and carbon dioxide. So ammonium carbonate's formula, if you recall, ammonium polyatomic ion has +1 charge, and carbonate polyatomic ion is CO3 with a 2 charge. So ammonium carbonate is NH4 twice CO3, and it is strongly heated to form ammonia, H2O, and CO2. Let's balance it. You put a 2 in front of N, and hydrogen 6, 7, 8, and you have 3 carbons, and it's all balanced. This is your net ionic equation. In decomposition equations, generally, because of the high heat, nothing is dissociated. Even if it is a salt, there is no water in the system in aqueous form to make it an aqueous solution, so you don't dissociate. Potassium chlorate. Now you know when the chlorates are heated, potassium chlorate is KClO3, and when you heat it up strongly, the bullet point dictates that chlorates form a chloride compound and oxygen. To balance it, you put a 2 here and a 3 here, and this is the net ionic. Note here, KCl can dissociate. Remember, all alkali metal ions containing compounds are soluble. But what's the condition? It should be present in aqueous form. There is no water here to change it to aqueous form. So in decomposition reactions, even though KCl has the capability to dissociate into K plus Cl minus, it will not because there's no water present in the system to dissociate it. The last one is sodium bicarbonate, NaHCO3, strongly heated. And the bullet points tell you that bicarbonates, when you heat them, they form sodium carbonate, carbon dioxide, and water. And let's see if these are balanced. And this is all balanced. So that is the net ionic equation for decomposition of sodium bicarbonate. Now let's look at some of the single replacement reactions practice problems. Solid calcium is added to hydrobromic acid solution. Now hydrobromic acid is a strong acid, so it will form calcium bromide CaBr2. Why Br2? Because calcium has 2 plus charge, Br has -1. When you crisscross, it is CaBr2 plus H2. So if you put a 2 here, it is balanced. Now the question is, how do you write net ionic equation? This word solution here means it's aqueous. That means calcium stays like this, but HBr, being a strong acid, will dissociate into H plus Br minus. And if you were to look at solubility rules, calcium bromide can dissociate. And bromide becomes spectator ion. So really ultimately calcium plus 2H plus gives you calcium 2 plus plus H2 is your net ionic equation here. The third sample here is, actually the second one. Calcium is added to water, and I'll let you write that because that is given over here, and you can see that this is the same reaction. Solid copper is added to silver nitrate solution. Solution means it's aqueous, it will dissociate. Copper will replace silver, form copper nitrate. Now here there is a big question. Copper forms +1 and +2 state. Which one would you form here? Because this one was neutral copper atom. The more common oxidation state is prevalent, and for copper it's 2+. How would you know that 2+ is more prevalent copper state? It is given in a periodic table, the purple periodic table that I've given you. Otherwise you can Google it and figure out if it is a variable valency cation, which state is more common. So here you'll make 2+, and then you'll make silver. that goes out, so you put a 2 here, 2 here, and now it is all balanced. For the net ionic, copper stays as such, silver ions break, nitrate break, it forms Cu2 plus and 2 NO3 minus and 2 Ag plus, and then nitrate and nitrate cancel out, so net ionic is Cu plus 2 Ag plus gives you Cu2 plus 2, I'm sorry, Ag, not Ag plus. This is just metallic silver. And this is the net ionic equation. And if you recall, I had said that most of the single replacement reactions are redox, and you can see basically electrons are being transferred from copper atom to silver ion, and copper changes to copper ion, and silver goes back to being solid silver. So metal atoms are present as solids, so deposits, they don't dissolve. But ions of the metals form ionic compounds, and if solubility rules dictate, they can be soluble or insoluble. Now moving on to some double replacement reactions here. And let's, oh, I went too far. So the double replacement reactions, let's see if there are some sample problems here. Lead nitrate, a solution of lead 2 nitrate is mixed with potassium sulfate. So PbNO3 twice, lead 2 nitrate with K2SO4, potassium sulfate. Remember, to write these formulas, you need to know your polyatomic ions and their charges, so you can crisscross and write the formula. Now they'll switch partner, forming lead sulfate and potassium nitrate. Please note, even though there was a 2 subscript here, this 2 was there because sulfate's charge was 2 minus. But in potassium nitrate, you wouldn't have a 2 as a subscript because potassium's charge is +1 and nitrate's charge is -1. When they crisscross, it's K1, NO3 1, and we don't write ones in chem. And to balance, you put a 2 in front. So remember, to balance an equation, you can change the coefficients, but you cannot change the subscripts. Subscripts come from the charge of the ions. Now this is a balanced equation. To write the net ionic equation, you'll cancel out the spectator ions, and ultimately your net ionic equation here is lead ion plus sulfate ion form lead sulfate precipitate. Let's take one more sample problems, which is pretty interesting. It says equal volumes of 0.1 molarity sodium phosphate is added to hydrochloric acid. So you have sodium phosphate and you're adding hydrochloric acid to it. Ideally, what you try to do is form sodium chloride and H3PO4, right? Well, if you do that, you have a little problem. What's the problem? To balance it, you get a 3 here and a 3 here. Now, sodium phosphate and HCl are reacting in a 1:3 ratio. But they say equal volume of equal molarity, meaning that if the volumes are equal and their molarities are equal, I should have written 0.1 molar hydrochloric acid here. If the volumes are equal and molarities are equal, meaning they are in 1:1 mole ratio. So this 1:3 mole ratio will not work. So what you'll have to do here is Na3PO4 and keep HCl at 1. And what will it form? HPO4 2 minus plus NaCl. Okay, so it'll be Na2HPO4 here and NaCl. So let me write it first in this form, Na2HPO4 plus NaCl. So this is all balanced. To write the net ionic, you cancel out Nas and Cl minus. So ultimately the net ionic is PO4 3 minus plus H plus. Note the 1:1 mole ratio gives you HPO4 2 minus, and that's the net ionic equation here. The next one is ammonia reacts with acetic acid. Remember, both of these are weak acid, weak bases, so will not dissociate anything, and when acid and base combine, they form a salt. So they'll form ammonium acetate. and because it's a salt, it will break apart in ammonium ion and acetate ion, so the net ionic equation will be this. So that's double replacement reaction. And combustion reactions are rather simple. You add oxygen to whatever is being combusted. Then redox reaction and complexation we will deal with the chapters when we are doing redox chapter and when we are doing complexation. So right now the focus is on first 5 types of reactions, and I hope through this podcast you learn how to write net ionic equations. Ultimately it is all about practice. Please do a lot of practice on writing net ionic equations. Thank you for listening.